go from current slide. Oh, wow. That started right up without any 3, 2, 1 that I saw. Okay. Any questions on anything we've done so far? And I told you all last time that there may be a Monday coming up that I have to be out, but I'll let you know when it gets closer. We were in Chapter 1, Introduction to Differential Equations, 1.1 Definitions and Terminology. We hopefully will finish this today, okay? It's been long enough. Example 9, using different symbols. That's a strange way to identify a problem. Here's a function. Let me get my pen set up. Okay. X is equal to C1 cosine 4t. Okay. And X is equal to C2 sine 4t. Okay. Where C1 and C2 are arbitrary constants. Okay. Or parameters. Okay. They're both solutions for this differential equation. X double prime plus 16x is equal to 0. All right. Let's make sure they're true on that. Okay. How do we check that? Take that first equation, and what would you do to it? Take a derivative. So x prime would be equal to okay, certainly got a C1 in it. A 4 C1. Second. Okay, certainly going to have a sine 4t in it, and with a minus sign, all right? Because derivative of cosine is minus sign. Continue. X double prime would be okay. Okay, it'll be a minus 16 C1 cosine 4t. And sure enough, if you plug that in this equation here, you get minus 16 C1 cosine 4t plus 16 times x, well, x is C1 cosine 4t. That adds to 0, because minus 16 plus 16, everything else being the same, that's 0. Let's see if the second one works. X prime here is equal to help me. Doing the second one here. Is what? 4 C2 cosine 4t, and x double prime would be negative 16 C2 sine 4t, and sure enough, you plug that into here, you get negative 16 C2 sine 4t plus 16 C2 sine 4t, that equals 0. Yeah, both of those work. For any constants, C1 and C2. Completely arbitrary. Okay? And they just did what we did. I'm sorry, I didn't know they were going to do the same thing. Finally, it's straightforward to verify that the linear combination of the solutions, or the two parameter family, your total solution, or pretty much would be x is equal to C1 cosine 4t plus C2 sine 4t, where C1 and C2 are arbitrary constants. If you went back and did your derivatives, the first term will give you exactly what you did before, the second term will give you exactly, you'd be 16, yeah, it works out exactly the same. Now, what they're getting at here, without really saying it yet, but it seems like they've said it before, if you have a second order differential equation here, you're going to need two parameters. Now, you get one that works, another one that works, then a linear combination of those two will also work. If you get another one that works, it's probably going to be some combination of these two anyway. Okay, so all you need is two. Okay? Now, they're going to go to a slightly different kind. I don't know if you remember back when we probably hit this in pre-calculus or somewhere back there, when they started talking about piecewise defined functions. That's what we're going to do now. Do y'all need this any longer? Okay. A one-parameter family of quartic monomial functions is y is equal to cx to the fourth. Okay? They say that's an explicit solution for the linear first order equation xy prime minus 4y is equal to 0. Okay? On the interval minus infinity to infinity. For all real numbers, x's, that should work. Okay? We need to verify that. So what would we need to do? Take a derivative. So it'll be y prime is equal to 4cx to the third. Perfect. Okay? So now let's plug it in. X times y prime, which is 4cx cubed, minus 4 times y, which is cx to the fourth. Is that equal to 0? Well, this one, when you multiply through, you get 4cx to the fourth minus 4cx to the fourth, and sure enough, that is indeed identically equal to 0. So, you verified that solution works. Okay? Now, what they show in the text, that when c is equal to, and remember, any arbitrary coefficient, let's just choose the simplest one, 1. Well, 0 would be simple, but that would be pretty uninteresting. Let's do 1, okay? Now, if y is equal to x to the fourth, here would be a solution, okay? The graph of a solution for c is equal to 1. No, I hit the wrong thing. I want my pen, but I want to do this in blue, so I'll match the book. Okay? I'm really big on matching the book. If this is plus 1, minus 1, plus 1, plus 2, plus 3, plus 4, whatever. Okay? When c is equal, when c is equal to 1, x equal 0, y is equal to 0. X equal 1, y is equal to 1. X equal minus 1, y is equal to minus 1, right? You go to x equal 2, and suddenly you're up there at 2 to the fourth power is 16. You're off scale really fast, okay? So that means this comes down very rapidly, bottoms out rather longly and then goes right back up again. It looks sort of like a parabola, but it hangs around 0 a bit longer, and it goes up much steeper after plus or minus 1. That's what a quartic does. A 6 would go even faster. 8 would do even more. But if you chose C equal minus 1, this is with C equal 1. When you choose C equal minus 1, you just flip that over on its head. Okay? That would be 0, 0. This would be 1 minus 1 and minus 1 minus 1. And then they go downhill from there too. So here they are coming up here very steeply, flattening out here, and then going down here again. Okay? So there would be when C is equal to minus 1. There's just to reflect that across the x-axis. All right. Now here's the thing that they're going to do, and it's a perfectly legitimate thing to do. My question is, who cares and why? Okay? Now, well, first, any other C is going to be some variation on this thing, with the positive C's being up here somewhere and the negative C's being down here somewhere. Okay? And they will spread out, get closer together, do a variety of things like that. Okay? But here's what they said. Here is another piecewise defined differentiable function that works. Let's take this part here, and then where it connects at 0 here, then take back off here. Whoops, I thought I got the blue. Yuck. And go like this. So that would be a piecewise defined function that y, this is your solution. Excuse me. I can't get the pen to come back up. There we go, it's there. Rather than y is equal to cx, you could do y is equal to minus x to the fourth anytime x was less than 0, and positive x to the fourth anytime x was greater than 0. Now, there's one thing I don't like about the rendition there, okay? And I think what they mean, because what they say later, you got to put an equal sign somewhere there, otherwise it's not defined as 0, okay? And you know it is, so usually we put it with the positive sign. They didn't in the text there, but then they did in the verbiage underneath the equation. It's also a solution, but cannot be obtained from a family C is equal to x to the fourth by a single choice of C. Okay? The solution is constructed from a family by choosing C1 for x greater less than 0 and C equal minus 1 for x less than 0 and C equal 1 for x greater than 0. But that is a legitimate thing to do. You can do that and have it work. So in this case, even though it's a first order differential equation, these are not independent arbitrary coefficients. They are coefficients that fit on a piecewise defined function. It's not like you have arbitrary C and then a different arbitrary C. You have two C's that are related to each other but each defined on a different piece. And that will also satisfy the equation, but it's just not your normal seepage. Okay? So then they have a little blurb on systems of differential equations. Up to this point we have been discussing single differential equations, containing one unknown function, but often in theory, as well as in many applications, we must deal with systems of differential equations, and that is when you have more than one function. Okay? And I think I'll go to a clean slate here for this one. If you had, let me go back to black. Okay. Though they kept in blue, dx dt is equal to some f of t, x and y, and dy dt is equal to some different function g of t, x, and y. Okay? Now your x's and y's are dependent variable. T is your one and only independent variable. A solution for such a system as this is a pair of differentiable functions. X is equal to phi1 of t, and y is equal to phi2 of t. Okay? Defined on the common interval I. They both must fit on the same interval I that satisfies each equation in the system. Now, they say that, and they don't really do anything else with it. Okay? But that's a system of differential equations. And there's nothing, they don't tell you any more about it or what you're going to be doing with this. What you might try to do is eliminate one variable or another and get down to just some function of t. And I imagine that's the way you work it. Because they don't give you any specifics, but if you can eliminate the by some type of manipulation, eliminate either the x or the y, one or the other in both of these, then you can probably go back and plug in and come up with some function. X is one function and y is a different function. But without any examples, they just say you can do it. A solution would be that. Now, your remarks here, and they get off into some of these things. An integral defined function is one that you might not be able to solve the integral, but you can write it as an integral defined function and still play with it that way and possibly find out, significant perspectives, by plugging in different values and maybe doing some graphs or other things like that. Now, sometimes those integral defined functions are non-elementary, okay? And the elementary functions they mention here are your constant functions, your polynomial functions, your rational functions, exponential functions, your log functions, the trig functions, and inverse trig functions. Just about anything beyond that are called your non-elementary functions that you might not have any way to integrate, differentiate, well, maybe differentiate, but you can't integrate them. Those are your non-elementary functions, okay? Now, they do some more things here on a variety of topics, but then they come up on the Roman numeral 6 in this little blurb at the end. I think they call it remarks. They give what they say is a general solution. If every solution of an nth order ordinary differential equation on an interval I can be obtained from an n parameter system, which makes sense, parameter family, g of x, y, c1, c2, all that equals 0, by appropriate choices of the parameters, c sub I is equal 1 to n, then we say that the family is a general solution of a differential equation. Later we'll come back and work more on what we mean by general solutions. But they introduce it here and then leave it for sections, and then we'll come back and get to it. But you can say you saw it first here. Homework exercises, same ones I've given several times before. Any of the odds 1 through 7 that are in the back of the book, 9 if it's in the back of the book, 11 or 13 if they're in the back of the book, 15 or 17 if they're in the back, 19 if it's in the back, either 21 or 23 if they're in the back, 25 or 27 if they're in the back, 29 if it's in the back, 31 or 33 if they're in the back, 35 if it's in the back, 37 or 39 if they're in the back, and 41 if it's in the back. Discussion problems most of the time are not in the back, but some of these may be worth a look. One in particular, number 51, talks about the folia of Descartes. There's a picture of it there. If that's something that you think may be a bit interesting to look at, you can either write on who in the world Descartes was, if that's what tickles your fancy, or how did he come up with this folio, what is it used for, is there any practical application of it, or is it just a neat little mathematical observation? Okay, you can look at any of the problems almost with those kind of lights, but that one specifically had a name associated with it. So that's all we got for 1-2, finally. 1-1, finally. So let's move on to 1-2. Initial value problems. Now they start with the most general case, and here's what it is. It's a pain in the neck to write. What if you had a differential equation that was your nth derivative is equal to some function of the variables x, that's your independent variable, y, that's the dependent variable, okay, from this time okay, nth order differential equation will then have derivatives in here, possible derivatives in here of your function of y prime, y double prime, y triple prime, y to the fourth, that's the fourth derivative of y, dot, 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 all the way up to and including the n minus 1, n minus first derivative of y. Okay? You won't ever have the next one because it's on the other side. Okay? So that gives that to you. Now, if this differential equation, nth order differential equation with function of n plus 1 variables, x, y, and then all those derivatives of y up to the n minus first derivative of y, will be subject to, and here's what that would be. Y at some value, I'm sorry, I can't write. Okay. get my pen to come back. There it comes, I think. All right. Subject to this, y evaluated at x0 is some value y0. Y prime, let's see, they put commas in between, y prime evaluated at the same value x sub 0. That's important here. Sorry. Is equal to some y1. Okay, now here we're having to change a little bit how we've been naming and numbering things. Y double prime at that same value x0 will then be y2. Y triple prime at that same value x0 is equal to y3. Yeah. Okay, and so on and so forth. Okay. Up to and including y, the n minus first derivative of y, at that same value, x0, is going to be some y of n minus 1. Okay? Now, just a little bit more nomenclature here. This is your nth order differential equations. On this side is the nth order derivative. On this side is some function of your independent variable x, your dependent variable y, and every derivative of the y up to the n minus first derivative of y, because the nth derivative is over here. Now, if you have this kind of an equation, then you may have these conditions that are to be met, subject to, and you pick a point for x, the independent variable, some value of x that you know the y at that x, the first derivative of y at that x, the second derivative of y at that x. I forgot. I thought I put my 1 down there, but it became a comma, didn't it? Okay. And these are not necessarily the same values here. That's why they put different subscripts on them. These subscripts match the order of the derivative. This is the 0th order, meaning just a function alone. This is the first one, second one. But you see, the subscripts don't really mean anything. It's just designating some value, not necessarily the same as the others. The x-zeros are all the same values. Okay. This is then called an initial value problem. Now, I have just a little problem with the name initial value. Being a physicist by training, to me, initial value means at time t equals 0. Your initial value when you're starting. And quite often that'll be the case when that's where you're beginning. If you've got a distance or a speed or acceleration problem or something like that, you'll know where you start, your initial conditions. They borrow that term and use it for any known condition. At some value x0, you know what all the values are. The first derivative, second derivative, the y value, everything, at that specific value. So it's not necessarily an initial value, it's some value, some given value. Okay. This is called an nth order initial value problem. I like to call it just IVP, okay? One reason I like that, I was a member of a Christian organization called InterVarsity Christian Fellowship, and their press was IVP, InterVarsity Press. And there's a lot of great books by IVP, so I like IVP. Okay, the values of y of x and the first n minus 1 derivatives are all evaluated at the same value, x sub 0, and these are called the initial conditions. Now, again, that doesn't mean they're always the first values. There's some common value of x, but you know all those conditions at that common value. All right. Now, when you're solving an nth order initial value problem, first you find an n parameter family of solutions. Because if you had this as a problem, you know you're going to have y is equal to some c1, say phi1 of x, plus some c2, phi2 of x, where these are all solutions to it, and you have n parameters. So you come up with an n parameter family of solutions. If you have an nth derivative, nth order differential equation, you're going to come up with n of those, a linear combination of n parameter system. Okay. Now, then using the initial conditions at each of these values, you take derivatives, you do whatever it is, and you evaluate at that value x0, where you know what the resulting value is, and you basically, for every one you plug in, you eliminate another c, okay? And by the time you do them all, you've got all of your c's identified, okay? Now, here's sort of a geometric interpretation of that. And let's see. Bill, you have a book or not? Yeah, okay. Okay, look thick enough to have, oh, and you have an ebook. So you can see what I'm talking about here, okay? Let me go and erase this. So let's say we have a second order, well, okay, we'll start with the easy one. First order differential equation. dy dx is equal to f of xy. Okay? There's the independent variable, dependent variable, no derivatives because this is your first derivative out here, so you don't have any. So your initial condition would be something like this, f of x0 is equal to y0. Just some value there. Okay, what that means geometrically is here you have a family of solutions. You have some solution here, some solution there. Each one of those things is a different value. When you, whatever your solution is here, you, it's pertinent over some part of the domain, okay? And if you know that at f of x0, y0, so if this is your x0 and you know the value here is y0, this is the parameter you use. That fixes, say, if this was C0, C1, C2, C3, C4, you choose C2 because that x, y point is on that curve. So that fixes it for you. Just the location of that curve. Now, what if you had a second order differential equation? d2y dx squared is equal to f of x, y, and y prime. Okay? And this is subject to y at x sub 0 is equal to y0, and y prime at x0 is equal to some y1. Okay? Zeros didn't look too good there. Now this you see, second order, you need two initial conditions. At the same point, x0, but two different ones. Well, in this case, here are your solutions, possible solutions here. You may have a solution up here, a solution here, a solution here, a solution here, a solution here. But if you know that at x0, you're at y0, but also that your slope, y prime at this x0, is here, then you know exactly where you belong. Okay? I find that second illustration a little less than satisfying because it looks like that one point is going to also tell you what. Not always the case. It could be that several points share that, but only one of them has the first derivative that's right. Okay? So I found their pictorial representation here a little less than satisfying because it could be that you had more than one curve that crosses the x0 at y0, y1 because you're goodness gracious, I can't think what to call it. Your initial condition, you might say, will fit one of those solutions, but not both of them. So you've got to have both of these fit, and then you know exactly which solution you have. You've eliminated both C's then, because this would have two arbitrary constants. By plugging this in and that in, you eliminate both, and you know exactly which solution that's going to be. Okay? Now, let's do example 1. Do we? Yeah, we have time, don't we? See, we go till 3:45. Yeah, okay. Got plenty of time, more than half an hour. Okay. So this would be a short week. I'm sure running out of energy quickly. All right. If you went back to your exercise 1.1, it said in problem 45, which is what function do you know from calculus is such that its first derivative is itself? I would say the e function. Its first derivative is a constant multiple of itself. Said, doesn't look like the same thing, but it says it. You were asked to deduce that y is equal to c e to the x. I'll say e to the x would have its own thing. Is a one-parameter family of solutions of the simple first order equation y prime is equal to y. Okay? Okay, all the solutions of this family are defined on an interval. This is on minus infinity to infinity. Okay? If we impose an initial condition, say that y of 0, now that looks like an initial condition to me, is equal to 3. There, say 3 and write 2. Something's wrong with these brain synapses. They just aren't working. Okay. Y of 0 is equal to 3. Okay? Then you plug in 0 for x and 3 for y. Okay, well here's your solution, and you say 3, that's your y, is equal to c e to the 0. Okay? All right, well we know that e to the 0 is equal to what? Say again?
C.
E to the 0.
Oh.
1, okay. So that would be 1. So you know that 3 is equal to c. Well, now you know that is, you go back and plug in here, y is equal to 3 e to the x. That solution will work for this differential equation with that initial condition. Okay? And it's the only one that will. Okay? That is a solution of the initial value problem, and it is the solution. Okay? But now if we demand that a solution curve pass through the point 1, negative 2, okay? So the B part, this is sort of the A part of the problem. Now if we demand that the solution curve pass through the point 1, negative 2, rather than 0, 3, then what we do is minus 2 being the y value. Let's see, let me write it in here a bit more generally. Okay. Y of 1 is equal to negative 2. That would then say that back up to this equation here, you would have that negative 2 is equal to c times e to the y. Okay? That would imply that c is equal to minus 2 over e. Okay? That is a number. It is not a particularly beautiful number, but it is a number. Okay? So then, there it is. I was trying to find it. Y is equal to negative 2 over e that's your c, e to the x. Okay? Now that's rather a strange way to write it, so let's write it this way. Negative 2 e to the minus 1 e to the x, which would then can be written as minus 2 e to the x minus 1. And that's how they write it. Okay? Now, all that's doing is changing away how it looks, but that's your result. There is your solution to the point, to this initial value problem. Different initial value problem, but it comes out being that solution. Okay.
Before we go on to example 2.
Yeah.
Example 1, suppose I give you 2 conditions on first order.
Right.
Necessarily must fit both of those conditions, or otherwise it's undefined.
Okay.
Okay. It must do both of those conditions, A and B.
Okay. Yeah. Now that's okay. Notice this is a first order, so it only has one parameter. So it can only fit one curve, okay? That is if your parameter was at 0, 3. This is if it's at 1, 2. If they were both, you have no solution. I mean, well, if you had a curve that went through both lines, then yeah, either one of those would have been equivalent. But these, the ones they show here, this solution and that solution are completely different solutions, okay? So it's either, if that's your initial condition, it's this one that is not. If you tried to force both of those in and they weren't on the same curve, then you have no solution. I mean, it's not a well-posed problem, okay? But this is showing, I'll just try to draw the graph of this generally, okay? CE to the x is going to look I'm sorry, I shouldn't have been above the line there. If this was your first solution, then this curve is this one right here, okay? But if your initial condition was this one down here, then this equation right here is the equation for that line. It can't be two of them unless the 2 points happen to be on the same curve. Then it'd be fine. It's just you chose one rather than the other, that would be fine. But if you had those 2 points, and this point will never be on exponential curve of that, because exponentials are always monotonic, okay? And they're either always negative or always positive. This one's always negative because of the -2 there. This is always positive because there's a +3 there. But they don't cross over, okay? So these 2 points, there's no single exponential curve that is going to match to. This one will match that one, this one will match this one. Now, if you had a second order differential equation, then you get a point and you get the slope for that point, that would then decide, because those are different orders, you know. Now, later we're going to get to what I think you're addressing here, and that would be a boundary value problem. You have this one at this point, that at that point, then you find the curve that goes through both of them. That's a trickier situation because you may have another curve that goes through both of those points, okay? That wouldn't be an exponential curve like this, but you could have something else that did that. That then is yet another bag of worms. But these 2 points will never fit on this equation because this one's positive and this one's negative. However, this point will fit on this curve and that curve only, okay? When your x of 0 is equal to 3, your c is 3. When your x of 0 is, when x is 1, y is -2, you're going to be, I didn't draw it right, but you know, that probably was down here. But that would be the curve that is on, and this curve is described on this. So, yeah, you wouldn't have these 2 points on the same exponential curve because they just wouldn't happen. But if there was some other function that did something like that, that could happen. But then those would be called boundary value problems because they're at different values. This is at 0, this is at 1. And those would be boundary value, which we're going to get to probably not today, but sometime in the future. Okay. So those are 2 first-order initial value problems, and they'll produce different results. Okay. Now, have we got, yeah. Here's a different example. This was problem 6 in exercises 2.2, which are chapters away, is a chapter away from here, so in the future. You will be asked to show that a one-parameter family of solutions of the first-order differential equation y prime plus 2xy squared is equal to 0, okay? That a one-parameter family of solutions for that differential equation is this. Y is equal to 1 over x squared plus c. Now, if we impose the initial condition that y of 0 is equal to minus 1, okay? If that's our initial condition, then what we have to do is go up here to our solution and say minus 1 is equal to 1 over c, right? Because you put a 0 in for x, 0 squared is 0, you get that. So this produces c is equal to minus 1, right? Okay, so then your solution for this differential equation with that initial condition is y is equal to 1 over x squared minus 1, right? Because you plugged in c of minus 1, right? Okay, now we could have, okay, I don't know if you remember, sometime in the not too distant past, we said that differential equations always are defined on some interval, okay? Now, those exponentials defined everywhere, negative infinity to positive infinity. This one, however, that equation is not defined everywhere. Where are places where it's not defined? X cannot equal plus 1 or minus 1. And fortunately, our x was neither one of those. Okay? So, this one, for x of 0 to be minus 1, you are limiting what interval this is good on. Okay? Because if you were to graph this, and they show it in the book, at x equal 1, you have a vertical asymptote. At x equal minus 1, you have a vertical asymptote. When x is equal to 0, you're down here at minus 1. There you are, okay? X equals 0, y is minus 1, okay? That's what we were told here, okay? Now, you also have, if you remember back in your pre-calculus algebra days, your horizontal asymptote is the ratio of the leading terms, which is 1 over x squared, which is basically y is equal to 0. So there's your horizontal asymptote, okay? And if you were to pick some other values here, when x is anything greater than 1, then this is going to be a positive number. You're going to be up there. If x is anything less than minus 1, this will also be a positive value. You're up there. And if x is anything between 0 and 1, you're down here. Okay? Because if you're between minus 1 and 1, x squared is less than 1, so this is going to be a negative number in the denominator, positive in the numerator, and the closer you get to 1, the closer you're getting to the thing. So this interval, this is only good on minus 1 to 1. Nowhere else. It could be something smaller than that, but it couldn't be good on minus 3 to 0. Can't happen because you can't cross this way. It can't include any place where the function is not defined. And this function is not defined there or there. So your interval of solution, your solution interval, has to be somewhere between -1 and 1. It could be less than that, like -1/2 to +3/4, or something like that. It could have a square bracket as long as it's not either of those two. These, they got to be parentheses. Okay. So.
I'm sorry, so understand -1 to 1
Right.
on the x-axis. That can be defined inside of that. But what about like from 1 to infinity? That's not.
Okay. Up there,
I'm sorry.
this point is not going to be on it.
Oh.
Yeah.
We're
That
going.
point will not be on that. If with another initial condition,
I forgot
you can come
about
at
that.
exactly that. Yeah.
I forgot
Exactly.
about the condition.
Yeah, that's the thing. Given another initial condition, you could still come up with this function, but it would be wherever that initial condition is on that portion. Okay. For C's that are positive, that could be defined everywhere, because C positive will be defined everywhere, so that could go. But if that C comes out being a negative number, you're going to have limitations. And your initial condition is going to be the thing that determines that, you know. So even though it might appear that this equation is good here, here, and here, with that initial condition, it's only good there, between -1 and 1, or something within that. Okay. And this is the point they're making. Considered as a function, with that thing right there being a function, this is the graph of the function. Okay? Considered as a solution for the differential equation, it could be any one of these intervals here, these three intervals. The whole thing is a solution for the function. Only one of those three intervals could be, but any one of them could be a solution for the differential equation. But for this initial value problem, you're limited to that one right there, because that's where their point is. And that's what they're trying to think here. Can't remember where it was, but they said any I can't remember. I think it's back on page 6. Any function phi defined on an interval I position, that may not be it. Oh yeah, down at the bottom. Interval of definition. You cannot think of a solution of an ordinary differential equation without simultaneously thinking the interval over which that solution is good. For this one that we had here, for that initial value problem, you're limited to that. Ooh, I'm knocking my screen to death. Okay. So that was their point there, and they really go overboard with it. Okay. Do we have time for example 3? Yes, yes, yes. So let's hit example 3. Back in example 9 of 1, now this is example 9 of 1.1, we saw that, and we did this one today, didn't we? X is equal to C1 cosine 4t, and X equal, plus, for the general solution, C2 sine 4t is a two-parameter family of solutions for this. X double prime plus 16x is equal to 0. And we've already shown that. We talked about it. Okay, done. Okay, find a solution of the initial value problem that meets this. Now this is a second order initial value problem, so how many conditions must you have? 2 at the same point. So here's the first one they give you. X at pi halves is equal to -2, and X prime at the same point, pi halves, is equal to 1. Okay? So there's your general solution. What would be still a solution of the initial value problem there? So what we do is plug and chug. So let's do it. Let's plug the first one in here. -2, that's your x value, is equal to C1 cosine of 4 times pi halves. And what's 4 times pi halves? 2 pi plus C2 times the sine of 2 pi. Okay? What's the sine of 2 pi? 0. So that one we don't get anything from, but we do get here that -2 is equal to C1, and what's the cosine of 2 pi? 1. So that's C1 is equal to -2. Well, that only gives us one of your parameters. So we're going to have to do the second one, which involves taking derivative of x. X prime, remember what that was? It's not hard to take again if you don't remember. -4 C1. Oh, well, we know what C1 is. C1 is -2. So let's go on and plug that in. Okay? -4 times -2 times cosine of, let's leave the 4t in there, 4t, and then do the next part. Derivative of the second part.
Oh, okay. We got negative.
And not that. Plus 4. C2. Okay, well, you let me mess that up, didn't you? This is a sine here. Okay. This is sine 4t. You take a derivative of cosine, got negative sine. And this will be cosine 4t. Okay? And now we know that x prime is going to be 1 at this same t equal pi halves. So that will then be, I'll write it down here, 1 is equal to 8, right? Times the sine of, well, 4 times pi halves is still 2 pi, plus 4 C2 times the cosine of 2 pi. But you remember what cosine of 2 pi was, right? And sine of 2 pi. This one's 0. So you have 1 is equal to 4 C2. Because cosine of 2 pi is 1, right? So what's C2? One-fourth. Perfect. So now your general solution is x is equal to -2 cosine 4t plus 1/4 sine 4t. That is the one, and perhaps only, but certainly one, solution for that differential equation, the y double prime, blah, 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 that fits those two initial conditions. Okay? This one came from that one. This one came from this one. Now, not always will they work out that way. It may be that you could have two equations, two unknowns, and you have to solve those to get what those are. this one, it just happened to be that when you plugged in pi halves for t, one of the, always the sine of 2 pi is going to go to 0, so you're left with just solving for the other. But sometimes it will be a little more involved with that, but still you get two solutions. And that is the one and only, I want to say, is still, they say, is a solution. X equal minus 2 cosine 4t plus 1/4 sine 4t is a solution for 4, equation 4, which is the one we had at the beginning. Now, do you think we have time for existence and uniqueness? Two fundamental equations arise. Now, if you notice, they kept saying is a solution. They are not saying the solution. So that's what we're getting to next. Two fundamental questions arise considering an initial value problem. Does a solution of the problem exist? Is one question. If a solution exists, is it the only solution? Is it unique? For the first order initial value problems, number 2, that's that big long hairy thing that we wrote. I'm sorry. No, it isn't. It's a very simple one we wrote. First order initial value problem, we asked, does the differential equation dy dx equal f of xy possess solutions? Okay, that's the first. Are there any solutions? Okay, does a solution exist? And if a solution, do any of the solution curves pass through the point that we had as our initial value? Okay, x0, y0. That's the existence part. The second part is the uniqueness. Can we be certain that there is precisely one solution curve that passes through that point? x0, y0.
Question.
Yeah.
Can we look at that and tell that we have to go through the steps for the existence part?
I think you most of the time have to go through the steps. I can't say that there aren't going to be times you can look at it and say, yep, that's it. That's going to be the only one. I'm trying to think if that's, but I think you have to pretty much go through the steps to guarantee it's the one and only, if there is a one and only. So uniqueness, when can we be certain that there's precisely one solution curve? It said in examples 1 and 3, and I tried to point that out to you, the phrase a solution is used rather than the solution. The indefinite article a is used deliberately to suggest the possibility that any other solution may exist. At this point, it has not been demonstrated that there is a single solution for each problem. The next example illustrates an initial value problem with two solutions. Now, if you think back, to remember this one, we did example 10. You had C1 going up here, C minus 1 going here, and C that piecewise defined function here. All three of those would have fit the initial condition that 0, 0. They all three. So in that one, certainly there are more than one solutions that will fit there. Now, would there be more than one that fit here? Well, this one fit here and that one fit there. So it could be that there are others, especially if you allow piecewise defined functions there, which kind of is cheating to me, but because they have more than one C, and they're not uniquely different. So I don't know if we're going to have time to finish example 4. So you want to start there next time? Because on Mondays I can go over a little bit, but on Wednesdays I'm kind of stuck on time because I have to get to the other campus. So we'll start next time with example 4. Let's see what additional homework exercises. Oh, we almost finished 1.2. Okay. I think you can do number 1 if that answers is in the back. believe you can do 3 or 5 if those answers are in the back. And I think you can do either 7 or 9 if those answers are in the back. I think maybe you can do 11 or 13 if those answers are in the back. All right, we'll hold off on the further ones after that until we do a few more examples. Okay, so go through 13. Any questions? All right. This is terrible, only meeting once a week, isn't it? Yeah. Okay. And like I said, there's going to be a week coming up, not next week, but I believe the following week, where I'm going to have to be going on Monday for something that's, we're to evaluate one course, and it's supposed to take us all day. That's ludicrous. But they're having us go to Shelton State to do it. They'll probably talk to us for a while and just waste time. Why in the world couldn't they do it on a Friday when most of us don't have classes? Because the administrators don't want to do anything on a Friday, I think, is what my opinion is. Anyway,
Don't put that online.
I just recorded it. Okay. What can they do? Take away my birthday. Okay.